Greetings, everybody. So what I have here is a problem from my math lab that I think would be a good one for me to show you. I'm given a sequence going by this formula, and that is natural log into the third power plus 9 minus natural log 6 into the third power plus 11n. And I wanted to calculate some terms of this sequence just to get a feel for what it looks like. This won't be the end result of the problem. It's not going to be how I solve it, but I would like it to confirm whatever result I get. Okay, so first term of the sequence I find by letting n be 1 in this formula. So I'd get natural log 10 minus natural log 17. Okay, and that turns out to be, rounded to 4 decimal places, negative 0.5306. So that's the first term. The second term I let n be 2. The third term I let n be 3. The fourth term I let n be 4. And I see a pattern. These numbers don't look random to me. It looks like they're increasing and perhaps leveling off around 1.7 or 8, okay, somewhere in there. But to take that a little further, I even plotted these terms of a sequence on a graph so we can see even better by visual pattern that yes, every term in the sequence seems to be getting closer to something. They're progressively closer, one at a time, to something, and that something is whatever the sequence converges to. So like whatever this number is, see on my grid here, that's about 1.79 or 1.8. Every term of this sequence gets closer to that, and every term of this sequence is closer to that than all the terms that came before it. All right, so I would say the sequence seems to converge to about 1.79. I mean, I can't tell exactly looking at this with the numbers rounded, but it certainly looks that way. Okay, it looks like every term of this sequence is closer to negative 1.79 than all the ones that came before it, and there's no limit to how close they'll get to that number. Okay, now that's just something numerical. I use a calculator. I generated this graph, all to help me see what this thing actually looks like. But that doesn't prove it. That doesn't prove it converges, okay? Because this sequence goes on forever. And it might be that once you go past, let's see, this is the 14th term right there, which is about negative 1.79 or so. Once you get past that, you got forever to go, and things could change. This formula might start behaving very differently as n gets bigger and bigger, and we have forever to go, okay? So this is nice, and it gives me an instinct, I think, about what to expect, but doesn't prove anything. So let's prove it. So how can I prove that this sequence converges, okay, or has a limit? Those are two ways of saying it, to what turns out to be natural log 1 over 6. So let's go through this in steps. First, I think we should combine the logarithms, combine it into one thing. Rather than have two separate logarithms, let's combine it into one. The rule I use for that is a logarithm of any base of some number m minus the logarithm of the same base of some other number n is one single logarithm base b m over n. So these are both natural logarithms. They have a base of e. And so they are compatible with this rule. So this as one logarithm is natural log n third plus 9 over 6n third plus 11n. Okay, now if I can figure out what happens to this thing inside the logarithm as n goes to infinity, then I can figure out ultimately what the limit of this is. So I'm going to look at just the inside part. I'm going to look at just n to the third plus 9 over 6 n to the third plus 11n. Okay, and I'll use something called L'Hopital's rule to calculate the limit of that as n goes to infinity. So real quick, why am I trying to find of this thing, of this formula that I was given, why am I trying to find the limit as n goes to infinity? Because if that has an answer, if the limit as n goes to infinity for your formula that defines your sequence, if that limit is some number L, then the sequence converges to L. And all said and done, I'm expecting to get a number that's about negative 1.79. So how do we do this limit? We could use something called L'Hopital's rule for this limit. Oh, real quick, let me show you something I put on Canvas. Okay, so here's something I put on Canvas. It's found on the same page that you're seeing this video. And I've got some general rules for sequences and finding their limits, and I've got rules for specific types of functions. And this is L'Hopital's rule. It says if you're trying to find the limit as x goes to infinity of f of x over g of x, and f of x and g of x individually go to infinity, that's called an indeterminate form. Meaning that indeterminate form does not tell us the answer. We can't say infinity over infinity is 1 or something like that. Then the way you can calculate that limit, where initially you get this indeterminate form, is to reapply the limit in terms of the individual derivatives of each of those functions. And if you could repeat this if you need to. So back where I am, I say, okay, if n goes to infinity, n to the third power plus 9 will go to infinity by itself. And so will 6 into the third plus 11n. So that is an indeterminate form. L'Hopital's rule says if I have an indeterminate form, I can reapply that limit to the derivative of the top. What's the derivative of n third plus 9? 3n squared. Over the derivative of the bottom. What's the derivative of 6 into the third plus 11n? It's 18n squared plus 11. Now that's still an indeterminate form, so I can repeat L'Hopital's rule. There's your derivative of the top again and the bottom. But once I get here, I find that that algebraically reduces. The n's cancel. Now n's out of the question now. Now just this number is just 6 over 36, it turns out. As n goes to infinity, it's always 6 over 36. And then that reduces to 1 over 6. Okay? So, all right. I used combining the logarithms, and then I looked at just that interior expression. I used L'Hopital's rule. So what I found is that if n goes to infinity, as applied to this original formula that defines my sequence, ultimately, it looks like this, but that inside part becomes 1 over 6. Okay, so there's your limit. Natural log 1 over 6. Natural log of whatever number you're finding inside that logarithm, which is 1 over 6. Okay, so there you have it. That sequence, because we found the limit of it as n goes to infinity, converges to natural log 1 over 6. Okay, I got my calculator and I said, well, what's that number? Does that confirm what I'm seeing here, where it looks like every term gets closer and closer one at a time to about negative 1.79. So I got my calculator, natural log 1 over 6 is negative 1.7917. And that's what I would have expected. Okay, that's certainly what it looked like. My numbers here don't prove anything, but now looking back at them, I think that they're exactly what I would expect them to be.